Alright, in this podcast we're going to talk about strong and weak bases. Alright, so just like with strong acids, strong bases are also strong electrolytes and weak bases are weak electrolytes. That means that a strong base is going to completely ionize in solution, right? So we're going to make an OH minus and some positive ion, okay? And if I take a weak base like ammonia and I put it in solution, I end up with mostly ammonia in solution. Very little bit of the base has picked up a proton and become NH4+. Okay, so if I look at here's a list of a variety of bases. If I look at what's common here, all of my hydroxides are at the top and they are all strong. So most hydroxides of group 1 and 2 metals are going to be strong bases. Then I have two acids here of anions. The carbonate ion and the bicarbonate ions are both weak bases, as are two amine acids, bases, which are nitrogen-containing bases. So I have ammonia and I have pyridine. And they are all weak bases. All right, so let's go ahead and take a look at how we would go about figuring out the pH of a weak base. This is actually a strong base, calcium hydroxide, right? So let's find its pH. So first of all, I got to write the balanced equation. And here, because I have two hydroxides on the calcium hydroxide, I'm going to make two hydroxides for every 1 mole or 1 molar of calcium hydroxide. So the first thing I have to do is figure out what my concentration of my hydroxide is, and because for every one of these I'm going to get two of these, right, because of my balanced equation, so I got to multiply the 0.25 times 2 to get 0.5 molar of my base. And once I have my molarity of my base, all I have to do is to find the P of that, or the POH of that. I do negative of the log of the 0.5, and I get 0.301. Now that's the POH. In order to find the pH, I know the relationship between pH and POH is that they add up to 14. And because I know what my OH is, I can simply subtract, and I get a pH of 13.699. Okay, so here are some of my amine bases. They all have nitrogen in them. That's what makes them amine bases. But there's simple ones like ammonia, probably the most common weak base we're going to talk about. There's ethylamine, which has an ethyl group and an amine group. And then we have this ring structure called pyridine, which is mostly carbons in that ring, but it's got one nitrogen in there. All right, so they're all known as amines. Okay, so aniline is a weak base. It has a Kb, a very, very tiny Kb. And we want to know the hydroxide ion concentration of 0.2 molar aniline. Okay, so here is my balanced equation. I'm just going to call this substance B for base, and it's going to react with water. And the bases are going to act as a hydrogen ion acceptor. So I'm just going to show the formation of a BH+, which is the base with an H+ on it, in the hydroxide. Okay, so my equilibrium expression then is my products, BH+, plus the times the OH minus over just the base, because the water, of course, is a liquid, so I don't include that in the equilibrium expression. Okay, so I can set up an ice table, and initially I have 0.20 molar of the aniline solution and none of the ions. My balanced equation is minus x plus x plus x. So my equilibrium concentrations are shown here. Okay, so I can take that expression and plug in what I have from my ice table, and it end up with x squared over 0.2 minus x. I can make the assumption that this x is going to be much, much smaller than the 0.2 because my kb is so tiny. And so I end up with x squared over 0.2 is equal to my kb, which was given to me. It's 3.8 times 10 to the minus 10. So now if I multiply both sides by 0.2, I get x squared is equal to 7.6 times 10 to the negative 11th. Take the square root of both sides, and I end up with x equals 8.7 times 10 to the minus 6. Now that x is my hydroxide ion concentration, right? And that's what we're asking for in this problem. So we're going to use this concentration in the next problem. Okay. So now that we know the OH concentration, we're trying to find what is the pH of this problem. So go ahead and pause and try to answer that problem. Okay, so you should have gotten 8.94. We knew from the previous problem that the hydroxide ion concentration is 8.7 times 10 to the minus 6th. So the pOH is the negative of the log of that, and that gives us a pOH of 5.06. Because I know that pH plus pOH is 14, I can just subtract the 5.06 from 14, and I get a pH of 8.94. Now I could have also used the Kw expression, which is that H plus, concentration of H plus times OH minus is always going to be equal to 1 times 10 to the minus 14th if I'm at 25 degrees C, and I'm going to assume that I am because it doesn't tell me that I'm not. And because I know the OH concentration, I can put that into the equation and solve for H plus, and when I do that, I end up with an H plus of 1.1 times 10 to the minus 19th. So my pH is the negative of the log of that, which is going to be 8.94. So either way, I end up with the same answer. Okay, so the last thing we're going to talk about relative to bases here is that the weaker the acid, the stronger its conjugate base. And the stronger the acid, the weaker its conjugate base. So if I look here at something like ammonium, its conjugate base, which is relatively weak, its conjugate base is going to be pretty strong. But if I look up here at HCl, a very strong acid, its conjugate base is so weak that it's actually considered to be neutral. Now this is going to be important to us when we look at whether or not salts are going to be basic or acidic. Alright, so we're going to finish up with this question that says, which anion is the weakest base? So go ahead and pause and try to answer this question, then come back. Okay, so if we look at these, we have to recognize that we have 3 Kas and 1 Kb. So the Kb for option B is a very strong Kb, so it's a very strong base. So I have to compare my 3 Kas, and when I do that, what I see is HCl is the strongest acid. So if it's the strongest acid, its anion is going to be the weakest base. Okay, that's going to do it for us right there.